Now, in this lecture, we'll find out the radius of the big circle. In the drawing, we have a big triangle. Inside the big triangle, we have two circles and one square. The radius of the small circle is equal to 1 unit. Then the side length of this square is equal to 3 units. And our mission is to find out the radius of this big circle. Okay, so first of all, we define the vertex of the triangle as A. We define this vertex as B. We define this vertex as C. We define the point of tendency of tangent BC with the small circle as D. We define the touching point of the square with side BC as E. We define the second touching point of the square with side BC as F. We define the point of tendency of tangent BC with this radius as Q. We define the center of the big circle as P. We define the center of the small circle as O. We define the touching point of the vertex of the square with side AC as L. We define the point of tendency of this tangent with the big circle as point H. We define the point of tendency of tangent AC with the big circle as point K. And we define the point of tendency of tangent AC with the small circle as point M. And we define the point of tendency of the small circle with the square as point S. So we join points O and S together by a straight line. So here point O is the center of the small circle, point S is the point of the circle itself, therefore OS is the radius of the small circle that is equal to 1. Okay. And we have here rule number 1, that according to rule number 1, a tangent to a circle is perpendicular to the radius drawn to its point of tendency. So therefore, according to rule number 1, this angle will be equal to 90 degrees and this angle will be also equal to 90 degrees. Likewise, we have the radius OD that is drawn to the point of tendency. Therefore, according to rule number 1, this angle will be equal to 90 degrees and this angle will be also equal to 90 degrees. We know that all the angles inside the square are right angles, so this angle is equal to 90 degrees, this angle equals to 90 degrees. Likewise, those two angles inside the square are equal to 90 degrees. And here, according to rule number 1, here we have the radius PQ that is drawn to the point of tendency, therefore this angle will be equal to 90 degrees and this angle will be also equal to 90 degrees. Okay, so here we have also rule number 3, according to rule number 3, the sum of the angles on one side of a straight line is equal to 180 degrees. BC is the side of a triangle. It is absolutely a straight line. So if we focus on the upper side of the straight line BC, if we focus on the upper side of the straight line BC at point F, here the sum of the angles must be equal to 180 degrees. So which angles we have at the upper side of BC at point F? We have this angle that is equal to 90 degrees plus the missing angle. Here the missing angle must be equal to 90 degrees. Why? In order to complete the sum of the angles in the upper side of BC at point F to 180 degrees, this angle must be equal to 90 degrees. Likewise, if we focus on the upper side of BC at point E, here the sum of the angles must be equal to 180 degrees. So which angles we have at point E? At the upper side of BC at point E, we have this angle that is equal to 90 degrees. Therefore, the missing angle must be also equal to 90 degrees. So we found out that inside quadrilateral SOED, inside this small quadrilateral, we have 1, 2, 3 at angles. Okay. Therefore, the fourth angle must be also equal to 90 degrees. This angle must be also equal to 90 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Okay? So, quadrilateral SOED has 4 right angles. Therefore, quadrilateral SOED is a rectangle. I'll write it down. Quadrilateral SOED is a rectangle because it has 4 right angles. And we know that the opposite sides of a rectangle are equal to each other. That is to say, SO equals to ED. SO equals to ED. SO equals to ED. But SO equals to 1 unit. It is the radius of the circle. So we can write here that SO equals to 1. And from this equation, 1 equals to SO equals to ED. We will derive that ED is also equal to 1 unit. ED is equal to 1 unit. Okay? Likewise, according to the sum rule that the opposite sides of a rectangle are equal to each other, we get that SE equals to OD. SE equals to OD. But OD equals to 1 unit. It is the radius of the small circle. So we can write here that OD equals to 1. And for this equation, SE equals to OD equals to 1, we will derive that SE is also equals to, we derive that SE is also equal to 1 unit. Here, SE equals to 1 unit. SE equals to 1 unit. We already found out that ED is also equals to 1 unit. So actually we found out that quadrilateral SOED is not a rectangle but a square, because all of its sides are equal to 1. Okay, so here in the next step I will present to you rule number 2, and we will implement rule number 2 in our drawing. According to rule number 2, the lengths of two tangents from a common external point to a circle are equal. Here we have the common external point P. From the common external point P, we have two tangents to the circle, tangent PA and tangent PB. And according to rule number 2, they are equal to each other. That is to say, PA equals to PB. So we can implement rule number 2 in our drawing. Why? Because in our drawing, here we'll focus at point L. But before that, before we focus at point L, know that LE equals to 3 units because it is one side of square edge LFE that is equal to 3 units. SE equals to 1 unit, so LE minus SE is 3 minus 1, that is 2. So we found out that LS equals to 2 units. Now we will focus on the common external point L. From the common external point L, we have two tangents to the small circle, tangent LS and tangent LM. And according to rule number 2, they are equal to each other. That is to say, LS equals to LM. LS equals to LM, but LS equals to 2, therefore LM will be also equal to 2. LM equals to 2. Likewise, we will focus on the common external point C. For the common external point C, we have two tangents to the small circle, tangent CD and tangent CM, and according to rule number 2, they are equal to each other. That is to say, CM equals to CD. So if CM equals to X, then CD must be also equal to X because of the fact that they are equal to each other. Okay. So in the next step, we will implement the Pythagoras theorem on the right green triangle, triangle ECL. On the right green triangle, triangle ECL, my PT is the version for Pythagoras theorem. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Okay. So here the hypotenuse is LC, therefore the square of the hypotenuse will be LC squared. And it must be equal to the sum of the squares of the perpendiculars, that is to say it must be equal to LE squared plus EC squared. So found out that according to the Pythagoras theorem on the green right triangle, triangle ESL, LC squared equals to LE squared plus E squared plus EC squared. So LC, what is the value of LC? It is very easy to see from the drawing that the value of LC is 2 plus x. So if LC equals to 2 plus x, then LC squared will be equal to 2 plus x squared. And it is equal to LE squared. LE equals to 2 plus 1, that is 3. So LE squared will be equal to 3 squared, that is 9, plus EC squared. What is the value of EC? It is very easy to see from the drawing that EC equals to x plus 1. Okay, EC equals to x plus 1, therefore EC squared equals to x plus 1 squared. In conclusion, according to the Pythagoras theorem, we found out that 2 plus x squared equals to 9 plus x plus 1 squared. Here we will open the brackets on both sides of this equation, equation number 1, and we get that according to equation number 1, 2 plus x squared equals to 2 squared, that is 4, plus x squared, plus 2 times 2x, that is 4x, that is equal to 9 plus x plus 1 squared equals to x squared, plus 1 squared, that is 1, plus 2x. So here we have x squared on both sides of equation number 1, so x squared will get cancelled. So what is left from equation number 1 after we cancel x squared? In this side of the equation we left only 4 plus 4x. And the other side of the equation number 1 we have 9 plus 1 is 10, so it is 10 plus 2x. Here we subtract 4 from this equation number 1, and we get that according to equation number 1, 4 minus 4 is 0, so we have here 4x. That is equal to 10 minus 4 is 6 plus 2x. Here we subtract 2x from this equation number 1, and we get that according to equation number 1, 4x minus 2x is 2x. That is equal to 2x minus 2x is 0, so is equal to 6. So 2x equals to 6. Here we divide this equation number 1 by 2, and we get that according to equation number 1, x equals to 6 over 2, that is 3. So we found out that x equals to 3 units. You can write here that x equals to 3 units. And also here, x equals to 3 units. Okay. In the next step, we join points O and M together by a straight line. Here point O is the center of the circle, point M is the point of the circle itself, therefore OM is the radius of the small circle that is equal to R. We have the radius OM that is 1 to the point of tendency, therefore this angle equals to 90 degrees, and this angle will be also equal to 90 degrees according to rule number 1. In the next step, we'll join points C and O together by a straight line. And we'll prove that the two right triangles that we created here, that is to say triangle OMC, is congruent to triangle ODC. Repeat again, and prove that triangle OMC is congruent to triangle ODC according to side rule. So all the two white green triangles are congruent to each other. So it is triangle OMC congruent to triangle ODC. So first of all, MO equals to OD. They are both the radii of the small circle, therefore they are equal to each other. MO equals to OD. They are both equal to Y. It's the radii of the small circle. In addition, we have CM that is equal to CD. That is equal to 3 units according to rule number 2. And finally, CO is the common side that belongs to both triangles, so CO equals to itself. So we actually proved that the two three small white triangles can go into each other according to side rule. So I will write it down. Actually proved that triangle OMC congruent, this is the sign of congruent, to triangle ODC according to side rule. Okay, and from the fact that the two small green right triangles can go into each other, we conclude that those two angles are also equal to each other according to the rule that corresponding angles in congruent triangles are equal to each other. Those two triangles can go to each other, therefore the two corresponding angles must be equal to each other. So if we define one angle as theta, then the other angle must be also equal to theta because of the fact that they are equal to each other. Okay? So both those two angles are equal to theta according to the rule that corresponding angles in congruent triangles are equal to each other. Okay? In the next step, so we join points M and D together by a straight line. By joining points M and D together by a straight line, we create a triangle DMC. So according to what we did until now, we can easily say that CO is the angle bisector of angle C. CO is the angle bisector of angle C because of the fact that it bisects angle C into two halves. Each half equals to theta. Right? This angle equals to theta. And this angle also equals to theta. So I write it down. CO is the angle bisector of angle C. In triangle MDC. Triangle MDC. Okay. We'll join points P and K together by a straight line. Point P is the center of the circle, point K is the point of the circle itself, therefore PK is the radius of the big circle that is equal to R. We'll join points C and P together by a straight line. By joining points P and C together by a straight line, we created here two right big triangles. The next step we will prove that those two big right triangles are similar to each other. That is to say, we will prove that triangle PKC is congruent to triangle PQC according to side rule. Okay, so why those two triangles can go into each other? First of all, PK equals to PQ. For the move the radii of the circle, therefore they are equal to each other. So PK equals to PQ. They are both equal to R. In addition, if you focus on the common self point C, from the common self point C, we have two tangents to the big circle, tangent PK and tangent CK and tangent CQ. And according to rule number 2, they are equal to each other. That is to say, CK equals to CQ. CK equals to CQ according to rule number 2. And finally, PC is the common side that belongs to both triangles, so PC equals to itself. PC equals to PC is the common side that belongs to both triangles. So we actually proved that the two right big triangles can go into each other according to side rule. So I write it down. We actually proved that the right green triangle PKC congruent to the right big triangle PQC according to side rule. And from the fact that the two right triangles can go into each other, the two right big triangles, we derive that those two angles are equal to each other according to the rule that corresponding angles in congruent triangles are equal to each other. Those two big right triangles can go into each other, therefore the two corresponding angles must be also equal to each other. So if we define one angle as theta, then the other angle must be also equal to theta. Why? Because they are equal to each other. Okay, so here we'll join points K and Q together by straight line. So according to what we did until now, we can conclude that PC is also the angle bisector of angle C. So I write it down. PC is the angle bisector of angle C. Why? Because it bisects angle C into two halves, each half equals to theta. In triangle KQC. Repeat again. PC is the angle bisector of angle C in triangle KQC. And we already found out that CO is also the angle bisector of angle C. So, in conclusion, angle C is two angle bisectors, PC and OC. And here we have a claim that CO passes for point P. The angle bisector CO passes for point P. So I write down the claim. According to our claim, the angle bisector CO passes for point P. Okay, I'll repeat again. According to our claim, angle bisector CO, this angle bisector CO passes for point P. So, we'll prove our claim by the negative way. So, in a negative way, we will assume that the angle bisector CO doesn't pass for point P. Okay. Our assumption is that the angle bisector CO doesn't pass for point P. And here we'll get to a contradiction because our assumption, and due to the contradiction we will conclude that our assumption is incorrect. Therefore we'll have to derive from it that CO in this passes from point P. That is the process of the proof. So according to our assumption, here CO doesn't pass through point P. That is to say, points CO and P, they are not located on the same straight line. So according to our assumption, we have here two angles, angle DCE or DCO, that is equal to theta, repeat again. According to our assumption, we have this angle OCD or DCO, it doesn't matter, that is equal to theta. And it is very easy to see from the drawing that CD, here CD is part of BC. CD is part of BC, or CD is part of CB. Here CD is part of CB. Okay? And if CD is part of CB, it means that they both located on the same straight line. CD and CB, they are both located on the same straight line. Why? Because CD is part of CB. So I write it down. So I can write down that the straight line CD and CB are located on the same straight line. In the next step, I will draw the second angle, that is angle PCB. I will draw angle PCB. Okay. Second angle PCP. This is point P, so this angle PCB or angle BCP, it is the same. Okay. So this is the second angle that I draw. This is angle PCB. We've already found out that the legs BC and DC, they are both located on the same straight line. What about the second leg? PC and OC. Here we have the second leg, that is leg PC and leg OC. if CO doesn't pass through point P, then it is impossible that PC and OC will be located on the same straight line. But according to our assumption, CO doesn't pass through point P. Therefore, PC and OC are not located on the same straight line, according to our assumption. So we can write down that PC and OC, both those two legs, are not located on the same straight line. So in those two angles, we have one leg of those two angles are located on the same straight line. That is to say, leg DC is located on the same straight line, that is leg BC. But the second leg of those two legs, of those two angles, that is to say OC and PC, are not located on the same straight line. And whenever you have two angles that one leg of those two angles are located on the same straight line and the other leg are not located on the same straight line, they cannot be equal to each other. Okay? They can be equal to each other only if the second leg also are located on the same straight line. When the first angle is located on the same straight, when the first leg is located on the same straight line, then the second leg also must be located on the same straight line. Otherwise, they can never be equal to each other. But according to our assumption, the second leg is not located on the same straight line. Therefore, those two angles are different angles. So if this angle is theta, then this angle must be equal to alpha, and theta is not equal to alpha. So we found out that angle C has two different angle bisectors that bisect it into two different halves. And read again. We actually found out that angle C is two different angle bisectors that bisect it into two different halves, while the angle bisector OC bisect angle C into two halves that each half equals to theta, that is to say to theta and theta. The angle bisector PC, on the other hand, bisect angle C into two different halves that each half equals to alpha, so to alpha and alpha. And this is absolutely impossible. Why? Because if angle C equals to 30 degrees, then any angle bisector of this angle C that is equal to 30 degrees will and must bisect it only into two halves that each half equals to 15 degrees and 15 degrees only, and only 15 degrees and 15 degrees and only, and not to any other two halves. Okay, so we actually got, due to our assumption, the CO doesn't pass for point P, we arrived to a contradiction and the contradiction is that angle C has two different angle bisectors that bisect it into two different halves. It is impossible because angle C can be bisected only to one, actually one, to two halves that it cannot be bisected into two different halves. Okay, as I've already shown you the example. If angle C equals to 30 degrees, then the only two halves that angle C that is equal to 30 degrees can be bisected is 15 degrees and 15 degrees only, and not to any other two halves. Okay, and therefore, due to the contradiction, we will conclude that our assumption that angle bisector OC doesn't pass for point C is not correct. And therefore, we will conclude that the angle bisector CO passes for point P. We finished with the proof. So in the next step, we will focus on the small right triangle ODC, on the small right triangle ODC. This angle equals to theta. This angle equals to 90 degrees, therefore this angle must be equal to 90 degrees minus theta. So I write it down. Why? Because 90 degrees minus theta plus theta is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. This is the sum of the angles in any triangle. So this angle must be equal to 90 degrees minus theta. Likewise, if we focus on the right triangle PQC, this angle equals to 90 degrees, this angle equals to theta, then therefore this angle must be equal to 90 degrees minus theta. Exactly for the same reason that this angle equals to 90 degrees minus theta. Okay. So in the next step, we'll prove that triangle PQC is similar to the small green right triangle ODC according to angle similarity rule. So I write down that triangle, the big right triangle is triangle PQC. Is similar to the green right triangle ODC. So why those two right triangles are similar to each other? First of all, those two angles are both equal to 90 degrees minus theta, therefore they are equal to each other. So angle QPC, this angle in the right big triangle, is equal to this angle, that is actually angle DOC. Repeat again. Angle QPC is equal to angle DOC. They are both equal to 90 degrees minus theta, therefore they are equal to each other. In addition, those two angles are both equal to 90 degrees, therefore they are equal to each other. So I write it down, angle PQC is equal to this angle, that is actually angle ODC. Repeat again, angle PQC equals to angle ODC, they are both equal to 90 degrees, therefore they are equal to each other. And finally, here, this angle, angle theta, that is a common angle that belongs to both triangles, so angle theta equals to itself. So we can call to angle theta angle PCQ, and it is equal to itself. You can call to angle theta also angle OCD. So we actually proved that the two right triangles can run to each other according to angle similarity rule. Triangle PQC is similar, this is the sign of similar to triangle DOC according to angle similarity rule. And from the fact that the two right triangles are similar to each other, we derive that the following relationship exists between their sides. We will derive that PQ in the big right triangle over OD, the small green right triangle, is equal to QC in the big right triangle over DC in the small green right triangle. I repeat again, we conclude that PQ over OD equals to QC over DC. So here, PQ is the radius of the big circle that is equal to 1. OD is the radius of the small circle that is equal to 1. And it is equal to QC. What is the value of QC? QC equals to, here we have 3 plus 1. Here we know that one side of the square is equal to 3 units. Okay, so here QC is equal to 3 plus 1 plus 3 plus 3 plus 1 plus 3 is 7 plus QF. So QC equals to 7 plus QF, so we substitute QC by 7 plus QF over DC. What is the value of DC? Here, DC, it is not written clearly, but here we found out that DC that is equal to X, it is equal to 3 units. So I write it again. We have already found out that DC equals to 3 units. Okay, so here DC equals to 3 units. So we substitute DC by 3. So in conclusion, we found out that R equals to 3 plus QF over 3. So here we multiply this equation number 1 by 3. And we get it according to equation number 1. We R equals to 7 plus QF. Here we subtract 7 from this equation number 1, and we get that according to equation number 1, QF equals to 3R minus 7. Okay. Here we can write down in the drawing that QF equals to 3R minus 7. Okay. Because of the fact that the side length of the square is equal to 3 units, we will examine 3 different cases for the value of the radius of the big circle. The radius of this big circle can be less than 3 units. The radius of this big circle can be equal to 3 units exactly, and the radius of this big circle can be greater than 3 units. So we'll examine and analyze each case in order to find out what is the correct case that applies to our drawing. Okay, so we start with the first case, case number 1. If R is less than 3 units. So if R is less than 3 units, then we'll draw a circle with a radius that is less than 3 units, and we'll analyze the drawing. We know that the side length of the square is equal to 3 units, so here it will be higher than the radius. Here the radius PL, it is drawn to the point of tendency. You can see here, therefore according to rule number 1, this angle equals to 90 degrees and this angle will be also equal to 90 degrees. Actually, inside quadrilateral PLQF, we have 1, 2, 3 right angles. Therefore, the fourth angle must be also equal to 90 degrees. So inside quadrilateral PLQF, we have 4 right angles. Therefore, quadrilateral QLPF, PLQF, quadrilateral PLQF is a rectangle. Why? Because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So, therefore, in rectangle PLQF, we get that side PL must be equal to side QF. Side PL equals to side QF. Here, but PL equals to R, it is the radius of the circle, so you can write here that PL equals to R, and from this equation R equals to PL equals to QF, we will derive that QF is also equals to R. So from one side QF equals to R. From the other side we have already found out that QF equals to 3R minus 7. So from this equation R equals to QF equals to 3R minus 7, we will derive that R equals to 3R minus 7. Here we subtract R from this equation and we get that R minus R is 0, 3R minus R is 2R minus 7. Here we add 7 to this equation and we get that 2R equals to 7. We will divide this equation by 2 and we get that R equals to 3.5 units. While according to our assumption, R is less than 3 units. So R cannot be simultaneously less than 3 units and also equals to 3.5 units. So it is a contradiction, and due to this contradiction, we cancel case 1, that is to say, R cannot be less than 3 units. Okay. In the next step, we'll examine the second case, that R equals to 3 units exactly. So case number 2 is that R equals to 3 units exactly. If R equals to 3 units, then I will draw a circle with a radius of 3 units and we will analyze the drawing. Okay. We also know that the side length of the square is also equal to 3 units. Okay, so here the radius will be the same height of the square, same height. So they are both equal to 3 units. Here the radius that is equal to 3 units it is drawn to the point of tendency, therefore this angle will be equal to 90 degrees. So inside quadrilateral PLQF, we have 1, 2, 3 right angles. Therefore, the fourth angle must be also equal to 90 degrees. So we have 4 angles in quadrilateral PLQF, therefore quadrilateral PLQF is a rectangle. As we know that the opposite sides of a rectangle are equal to each other. So here, so in rectangle PLQF, side PL must be equal to side QF. PL equals to QF. But here, PL is the radius of the circle that is equal to 3 units. So from this equation, 3 equals to PL equals to QF, we will derive that QF is also equals to 3 units. So from one side, QF equals to 3 units. From the other side, we have only found out that QF equals to 3R minus 7. So from this equation, 3 equals to QF equals to 3R minus 7, we will derive that 3 equals to 3R minus 7. Here we add 7 to this equation and we get that 3R equals to 3 plus 7, that is 10. Here we divide this equation by 3 and we get that according to this equation, R equals to 10 over 3, that is to say R equals to 3 and a third. While according to our assumption, R equals to 3, so R cannot both simultaneously cannot be equal to 3 and also to 3 and a third. Therefore, we have a contradiction, and due to the contradiction, we cancel the second case, that is to say, R cannot be equal to 3 units. So we left only with the third case, that R is greater than 3 units. So if R is greater than 3 units, then I will draw a circle that is greater than 3 units. this is the radius of the circle that is greater than 3 units. So the radius will be higher than the square. Here from point H, we'll draw perpendicular on the radius PQ. Repeat again, from point H, we'll draw perpendicular on the radius PQ. So here, this angle equals to 90 degrees, and this angle will be also equal to 90 degrees according to our construction. We define the touching point of the perpendicular from point H and PQ as T. Here, inside quadrilateral THQF, we have 1, 2, 3 right angles. Therefore, the fourth angle must be also equal to 90 degrees. Therefore, quadrilateral THQF has 4 right angles. Therefore, quadrilateral THQF is a right angle because it has 4 right angles. And we know that the opposite sides of a rectangle are equal to each other. That is to say, here TQ is equal to HF. Again, TQ is equal to HF. TQ equals to HF. But HF equals to 3, it is the side of the square. So from this equation, TQ equals to HF equals to 3, we derive that TQ is also equals to 3 units. TQ equals to 3 units. Likewise, according to the same rule that the opposite sides of a rectangle are equal to each other, we get that TH is equal to QF. TH is equal to QF. But we have already found out that QF equals to 3R minus 7. And from this equation, TH equals to QF equals to 3R minus 7. We will derive that TH is also equal to 3R minus 7. TH is equal to 3R minus 7. TH is equal to 3R minus 7. What is the value of PT? The value of PT, here, it is very easy to see from the drawing that PT equals to PQ minus TQ. Again, PT equals to PQ minus TQ. Okay. So here I write it down. PT equals to PQ minus TQ. That is to say, PT is equal to PQ, that is the radius of the big circle, that is equal to R, minus TQ, that is equal to 3. So in conclusion, I found out that PT equals to R minus 3. PT equals to R minus 3. In the next step, we join points P and H together by a straight line. Point P is the center of the circle, point H is the point of the circle itself, therefore PH is the radius of the circle, that is equal to R. In the next step, I'll copy the right triangle PTH, this right triangle, in a new page, and we'll implement the Pythagoras theorem on this green right triangle PTH. Okay. PT equals to R minus 3, PH equals to 3R minus 7, and the hypotenuse PH equals to R, is the radius of the big circle. So this is the right triangle PTH that I copied from the original drawing. So we'll implement here the Pythagoras theorem. Here by PT is an equation for Pythagoras theorem. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, PH square is equal to PT square plus TH square. Okay. PH square is R square, and it is equal to PT square. PT is R minus 3. Therefore, PT square is R minus 3 square plus TH square. TH equals to 3R minus 7, therefore TH square will be equal to 3R minus 7 square. Here we will open the brackets on this side of equation number 1, and we get that according to equation number 1, R square equals to R minus 3 square is R square plus 3 square, that is 9, minus 2 times R times 3 is minus 6R, plus 3 minus 3R minus 7 square is 3R square, that is 9R square, plus 7 square, that is 49, minus 2 times 3R is minus 6R, and minus 6R times 7 is minus 42R. So here we have R square on both sides of equation number 1, so R square will get cancelled. In this side of the equation we have 0, that is equal to 9R square minus 6r minus 42r is minus 48r. 9 plus 49 is 58. So in conclusion, we got here the quadratic equation that 9r squared minus 48r plus 58 equals to 0. The general formula for a quadratic equation is ax squared plus bx plus c equals to 0. Here a, b and c are the coefficients of the quadratic equation, and x is the variable that we are looking for. And we find out the value of x according to the following formula, that x equals to minus b plus minus square root of b squared minus 4 times ac over 2a. In our specific quadratic equation, the coefficient a equals to 9, the coefficient b equals to minus 48, and the coefficient c equals to 58. And the variable that we are looking for is r, so x equals to r. So we put the data inside the formula for x and we find out the value of r because x equals to r. So we get that r equals to minus b, b equals to minus 48, therefore minus b is minus 48, that is plus 48, plus minus square root of b squared. B is minus 48, so b squared is minus 48 squared, that is 2304. Minus 4 times a is 9, minus 4 times 9 is minus 36, and minus 36 times c is 58, so minus 36 times 58 is 2088. All divided by 2a, a is 9, so 2a is 18. So here we will get that the radius of the big circle r equals to 48 plus minus 2304 over 2088 is 216 over 18. And here r equals to 48 plus minus the square root of 216 is 14.6969. So the radius of the big circle, we have here two possibilities for the value of the radius of the big circle. The radius of the big circle will be equal to either 48 minus 14.6969 over 18. And for 48 minus 14.6969 is 33.3031 over 18, so it is equal to 1.85. So I found out that the radius of the big circle equals to 1.85, but because of the fact that r cannot be less than 3 units and 1.85 is less than 3 units, we cancel this solution and we left only With the second solution, that the radius of the big circle R equals to 48 plus 14.6969 over 18. 48 plus 14.6969 is 62.6969 over 18. It is equal to 3.483 units. So we actually found out that the radius of the big circle, capital R, equals to 3.483 units. We finished to answer the question, so in the next step I'll summarize the lecture. Actually, in the drawing we have a big triangle. Inside the big triangle we have two circles and one square. The side length of the square is equal to 3 units, and the radius of the small circle equals to 1 unit. And our mission is to find out the radius of the big circle. In order to find out the radius of the big circle, we actually used in 3 rules all over the question. So I present you the 3 rules that we used in this question in order to solve this question. Okay. So, the first rule that we used is that a tangent to a circle is perpendicular to the radius drawn to its point of tendency. Here we have tangent AB is tangent to this circle at point M. Point M is the point of tendency, and we have the radius OM that is drawn to the point of tendency, and whenever we have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MO. So if AB is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle will be also equal to 90 degrees. Then I presented to you also rule number 2. According to rule number 2, the lengths of two tangents from a common external point to a circle are equal. Here we have the common external point P. For the common external point P, we have two tangents to the circle, tangent PA and tangent PB. And according to rule number 2, they are equal to each other. That is to say, PA is equal to PB. And then I presented to you rule number 3. According to rule number 3, the sum of the angles on one side of a straight line is equal to 180 degrees. Here we have the straight line CD. So if you focus on the upper side of the straight line CD point O, here the sum of the angles must be equal to 180 degrees. So which angles we have at the upper side of CD at point O? We have here angle alpha and angle beta. Therefore, alpha plus beta must be equal to 180 degrees. Okay. Then we actually used the 3 rules in order to prove that the small quadrilateral SOED is a rectangle. Okay, and we know that the opposite sides of a rectangle are equal to each other. That is to say, SO equals to ED. SO equals to ED. but here SO is the radius of the circle that is equal to 1. And for this equation, 1 equals to SO equals to ED, we derive that ED is also equals to 1 unit. Here, ED is also equals to 1 unit. Likewise, according to the same rule that the opposite sides of a rectangle are equal to each other, here SE is equal to OD. SE equals to OD, but OD equals to 1 unit. It is the radius of the circle. So for this equation, SE equals to OD equals to 1, we will derive that SE equals also to 1. So inside, so all the sides of quadrangle SOED are equal to each other. Therefore, quadrangle SOED is not a rectangle but a square. Okay. Then use rule number 2. Here we know that ES equals to 1 unit. LE is the side length of the square that is equal to 3 units. So LE minus SE equals to LS. So here LE is 3, SE is 1. So 3 minus 1 is 2 and LS equals to 2. Then we focused on the common external point L. From the common external point L, we have two tangents to this circle, tangent LS and tangent LM. And according to rule number 2, they are equal to each other. That is to say, LS equals to LM. But LS equals to 2, therefore LM will be also equal to 2. Likewise, we focused on the common external point C. From the common external point C, we have two tangents to this circle, tangent CD and tangent CM. And according to rule number 2, they are equal to each other. That is to say, CD equals to CM. So if we define CD as X, then CM must be also equal to X. Then we implemented the Pythagoras theorem on the right green triangle, triangle LEC. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, LC square equals to LE square plus EC square. Okay, again, in the right green triangle, triangle LEC, or ESL, LC square equals to LE square plus EC square. What is the value of the hypotenuse LC? LC is very easy to see from the drawing that LC equals to 2 plus x. Therefore, LC square will be equal to 2 plus x square, and it is equal to LE square. LE equals to 3. Therefore, LE square will be equal to 3 square, that is 9, plus EC square. EC equals to 1 plus x. It is not clear, so I read a lot of, so here LC, so here this is equal to x according to rule number 2 DC, so EC equals to 1 plus x, therefore EC square equals to 1 plus x square. So in conclusion, we found out that according to equation number 1, 2 plus x square equals to 9 plus x plus 1 square. We open the brackets on both sides of this equation, equation number 1, and we found out that according to equation number 1, 2 plus x square equals to 2 squared, that is 4, plus x squared, plus 2 times 2x, that is 4x, and it is equal to 9, plus x plus 1 square. X plus 1 square equals to x squared, plus 1 squared, that is 1, plus 2x. So here we have x squared on both sides of the equation, so x squared will get cancelled. So what is left from equation number 1 after we cancel x square? What is left is that in this side of the equation we have left with 4 plus 4x. In the other side of the equation we have 9 plus 1, that is 10, plus 2x. Here we subtracted 4 from this equation, equation number 1, and we found out that 4 minus 4 is 0. So in this side of the equation we left only 4x, and here 10 minus 4 is 6. So in this side of the equation we left with 6 plus 2x. Here we subtracted 2x from this equation, equation number 1. We found out that according to equation number 1, 4x minus 2x is 2x, and 2x minus 2x is 0. So in conclusion, we found out that 2x equals to 6 according to equation number 1. We divided this equation by 2 and we found out that x equals to 6 over 2, that is 3. So here x equals to 3 and here also x equals to 3. Then we join points M and O together by a straight line. So here point O is the center of the circle, point M is the point of the circle itself, therefore OM is the radius of the circle that is equal to 1. Then we join point C and O together by a straight line. In this way we created here two right green triangles, triangle OMC and triangle COD. Then in the next step we put that those two right triangles can point to each other according to side rule. I'll explain what I mean. Here MO equals to OD, they are equal to each other because they are both the radii of the circle, therefore they are equal to each other. In addition, according to rule number 2, CM equals to CD equals to 3 units. According, as I already mentioned, they are equal to each other according to rule number 2. And finally, we have side CO, that is a common side that belongs to both triangles, so CO equals to itself. So we actually found out that the two green right triangles can point to each other according to side rule. And for the fact that the two right triangles are similar to each other, we conclude that those two angles are equal to each other according to the rule that corresponding angles in congruent triangles are equal to each other. So if one angle equals to theta, then the other angle must be also equal to theta because of the fact that they are equal to each other. Okay, so then we join points P and K together by a straight line. Point P is the center of the circle, point K is the point of the circle itself, therefore PK is the radius of the circle, the big circle that is equal to 1. But before that, according to what we did until now, we can conclude here. We joined points M and D together by a straight line. In this way, we created triangle MDC. We can conclude from according to what we did until now that CO is the angle bisector of angle C. Why? Because CO bisects angle C into two equal angles, theta and theta. And repeat again. CO is the angle bisector of angle C in triangle MDC. Then we join points P and K together. As I already mentioned, PK equals to R, and we prove that those two right triangles can point to each other according to side rule. I will explain what I mean. Here PK equals to PQ. Why? Because they are both the radii of the circle, therefore they are equal to each other. In addition, if you focus on the common external point C, from the common external point C, we have two tangents to the big circle, tangent CK and tangent CQ. And according to number 2, they must be equal to each other. That is to say, CK equals to CQ. And finally, we have angle side CP that is a common side and belongs to both triangles, so CP equals to itself. So actually prove that those two right triangles are similar to each other according to side rule. And from the fact that they are similar to each other, we derive that those two angles are equal to each other. According to the rule that corresponding angles in congruent triangles are equal to each other. So if one angle equals to theta, then the other angle must be also equal to theta. Then we join points K and Q together by a straight line. So until this stage, we can conclude that PC is the angle bisector of angle C. Why? Because it bisects angle C into two equal angles in triangle KQC. Here, here PC is the angle bisector of angle C in triangle KQC, therefore angle C is two angle bisector, PC and CO. We bisect angle C into two equal halves, theta and theta. Then we have a claim that CO passes for point P. CO passes for point P, so until again, CO passes for point P. We prove this claim in a negative way. That is to say, we actually assumed that CO doesn't pass for point P, and according to our assumption we got to a contradiction. Therefore we concluded that our assumption was the incorrect assumption. Therefore CO indeed passes for point P. Okay, this was the process of the proof. So in the first step we actually assumed the negative way assumption that CO doesn't passes for point P. So if CO doesn't passes for point P, then we will have here two angles, angle OCD that is equal to theta. It's very easy to see from the drawing that CD and BC lie on the same straight line. Why? Because CD is part of BC. If CD is part of BC, it means that CD and BC must lie on the same straight line. It is very easy. Okay, here can conclude from it that CD and CB lie on the same straight line. Why? Because CD is part of BC. Then I copied the second angle, that is angle PCB. This is angle PCB, and as I already mentioned before, BC and CD lie on the same straight line. What about the second leg of the two angles? We have the second leg in this angle is OC, the second leg of this angle is PC. According to our assumption, CO doesn't pass for point P. If CO doesn't pass for point P, it means that CO and CP lie on different straight lines. If CO doesn't pass for point P, it means that CO and CP lie on different straight lines. Otherwise, if they lie on the same straight line, CO must pass for point P. Okay? So here, PC and CO are not located on the same straight line according to our assumption. So if we have two angles that one leg of them is a common leg or lie on the same straight line, and the second leg doesn't lie on the same straight line, they can never be equal to each other, because if one leg lie on the same straight line, then the other leg must also lie on the same straight line in order that the two angles will be equal to each other. But according to our assumption, the second leg doesn't lie on the same straight line. Therefore, those two angles can never be equal to each other. That is to say, if angle DCO equals to theta, then angle PCB must be another angle, alpha, and alpha doesn't equal to theta. Okay? So actually, we found out that angle C is two different angle bisector that bisect it into two different halves. That is to say, while angle bisector OC bisect angle C into two halves that each half equals to theta, that is to say to theta and theta, angle bisector PC bisect it into two different halves that each half equals to alpha, so it is alpha and alpha. But it is impossible. Why? Because if angle C is equal to 30 degrees, then any angle bisector of angle C that is equal to 30 degrees will bisect it to only 15 degrees and 15 degrees only, and not to any two other halves. But here we found out that it bisects angle C into two different halves. That is impossible. Okay, so you got a contradiction, and due to this contradiction, we must conclude that our assumption is not correct. Our assumption that OC doesn't pass through point P is not correct. Therefore, we must conclude that OC indeed passes through point P. We finish with the proof. Then we focus on triangle ODC, the small green right triangle. This angle equals to theta. This angle equals to 90 degrees. So the third angle must be equal to 90 degrees minus theta. Why? Because 90 degrees minus theta plus theta is 90 degrees, and 90 degrees plus 90 degrees is 180 degrees. That is the sum of the angles in any triangle. Likewise, in the big right triangle, triangle PQC, this angle equals to theta. This angle equals 90 degrees, therefore this angle must be equal to 90 degrees. Then we prove that those two triangles are similar to each other according to angle similarity rule. Why? I'll explain now why. Those two angles, they are both equal to 90 degrees minus theta, therefore they are equal to each other. In addition, those two angles, they are both equal to 90 degrees, therefore they are equal to each other. And finally, we have angle theta that is a common angle, it belongs to both angles, so angle theta equals to itself. So actually we found out that those two right angles are similar to each other according to angle similarity rule. And for the fact that those two right angles are similar to each other, we conclude that the following relationship exists between their sides. We will conclude that PQ over OD equals to QC over DC. Repeat again, we conclude that PQ over OD equals to QC over DC. PQ is R, OD is the radius of the small circle that is equal to 1. What is the value of QC? For the moment it is very easy to see that QC equals to 3 plus 1 plus 3, that is 7, plus QF. QC equals to 7 plus QF, therefore we substitute QC by 7 plus QF over DC. It's very easy to see from the drawing that DC equals to 3 units. So we substitute DC by 3, and finally we found out that R equals to 7 plus QF over 3. Here we multiply this equation by 3, and we found out that 3R equals to 7 plus QF. Here we subtracted 7 from this equation number 1, and finally we found out that QF equals to 3R minus 7. So we can write down here in the drawing that QF equals to 3R minus 7. And because of the fact that the side length of the square is equal to 3 units, we examined 3 possibilities for the value of the radius of this big circle. The radius of this big circle could be equal could be less than 3 units, or the radius of this big circle could be equal to exactly to 4 units. And the first possibility is that the radius of this big circle will be greater than 3 units. So according to the first case, if R is less than 3 units, then we will have this drawing. You can see here that the side length of the square is 3 units, and because of the fact that the radius is less than 3 units, then the side length of the square is higher than the radius. Okay? So here inside quadrilateral PLQ, PLQ, inside quadrilateral PLQF, inside this quadrilateral PLQF, we have 1, 2, 3 right angles. Why? Because if this angle equals to 90 degrees according to rule number 1. So inside this quadrilateral we have 3 right angles, therefore the fourth angle must be also equal to 90 degrees. So quadrilateral PLQF has 4 right angles, therefore it is a rectangle. And we know that the opposite sides of a rectangle are equal to each other. That is to say, PL is equal to QF. PL equals to QF. But according to this drawing here, PL is the radius of the circle that is equal to R. So we can write here that PL equals to R, and from this equation R equals to PL equals to QF, we derive that QF is also equals to R. QF equals to R. From one side QF equals to R. From the other side we have already found out that QF equals to 3R minus 7. So from this equation R equals to QF equals to 3R minus 7, we derive that R equals to 3R minus 7. Here we subtract from this equation R minus R is 0 and 3R minus R is 2R. So here in conclusion we found out that 2R minus 7 equals to 0. We added 7 to this equation and we found out that 2R equals to 7. We divided this equation by 2 and we found out that R equals to 3.5 units. But according to our assumption, R is less than 3 units. So R cannot simultaneously be equal to 3.5 units and will be less than 3 units. It is a contradiction. Due to the contradiction, we cancel this possibility, that is to say R cannot be less than 3 units. Then we examined the second possibility, that R equals to 3 units exactly, therefore we will have this drawing, because here we have the side length of the square that is equal to 3 units, it is equal to the radius that is also equal to 3 units. Okay, so here we have the radius that is drawn to the point of tendency, therefore this angle equals to 90 degrees. So inside quadrilateral PLQF we have 1, 2, 3 right angles, therefore the fourth angle must be also equal to 90 degrees. So quadrilateral PLQF that has 4 right angles will be a rectangle, and we know that the opposite sides of a rectangle are equal to each other. That is to say PL equals to QF. PL equals to QF, but here PL equals to 3 units. It's the radius of the circle that is 3. And from this equation 3 equals to PL equals to QF, we will derive that QF is also equal to 3 units. So from one side QF equals to 4 units, and from the other side we have already found out that QF equals to 3R minus 7. So from this equation 3 equals to QF equals to 3R minus 7, we will derive that 3 equals to 3R minus 7. So here we added 7 to this equation and we found out that 3R equals to 7 plus 3, that is 10. We divided this equation by 3 and we found out that R equals to 3 and a third. So according to our assumption, R equals to 3. So R cannot simultaneously be equal to 3 and also to 3 and a third. So it is a contradiction, therefore due to the contradiction we cancel the possibility that R equals to 3. Therefore we left only with the third possibility, that R is greater than 3 units. If R is greater than 3 units, then we will have this drawing. You can see here that the radius of this circle that is greater than 3 units, it is higher than the side length of the square that is equal to 3 units. Okay. So here, from point H, we draw perpendicular on PQ. Again, from point H, we draw perpendicular on PQ. This is the radius of the big circle. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. So in quadrilateral THQF, TQF, we have 1, 2, 3 right angles, therefore this fourth angle must be also equal to 90 degrees, and therefore quadrilateral THQF is a rectangle, and we know that the opposite sides of a rectangle are equal to each other. That is to say, TQ is equal to HF. TQ equals to HF, but here HF is the side length of the square that is equal to 3 units. So we can write here that HF equals to 3, and from this equation TQ equals to HF equals to 3, we will derive that TQ is also equals to 3 units. Here TQ equals to 3 units. Likewise, according to the same rule that the opposite sides of a rectangle are equal to each other, we get that TH equals to QF. TH equals to QF, but here we have only found out that QF equals to 3R minus 7, so we can write here that QF equals to 3R minus 7, and from this equation TH equals to QF equals to 3R minus 7, we will derive that TH is also equal to 3R minus 7. And what is the length of PT? It is very easy to see from the drawing that PT equals to PQ minus TQ. Again, PT equals to PQ minus TQ. Here, PT equals to PQ minus TQ. Okay, so PT equals to PQ, that is R, minus TQ, that is 3. So in total, we found out that PT equals to R minus 3. Then I copied this green right triangle PTH in a new page, and we implemented the Pythagoras theorem on this right green triangle PTH. So actually, this is the right triangle PTH that I copied from the original drawing. We implemented the Pythagoras theorem. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, PH square equals to PT square plus TH square. Again, PH square equals to PT square plus TH square. PH square is R square. It is equal to PT square. PT is R minus 3, therefore PT square is R minus 3 square plus TH square. TH is 3R minus 7, therefore TH square is 3R minus 7 square. So in total, we found out that according to equation number 1, R equals to R minus 3 square plus 3R minus 7 square. We opened the brackets on this side of equation number 1, and we found out that according to equation number 1, R square equals to R minus 3 square. R minus 3 square equals to R square plus 3 square, that is 9, minus 2 times R times 3 is minus 6R, plus 3R minus 7 square. 3R minus 7 square is 3R square, that is 9R square, plus 7 square, that is 49, minus 2 times 3R is minus 6R, and minus 6R times 7 is minus 42R. Here we have R square on both sides of the equation, so R square will get cancelled, and we left only with 0 in this side of the equation, and the other side of the equation we have 9R square, and here we have minus 6R minus 42R is minus 48R, 9 plus 48 is 58. So in conclusion, found that we have here, according to equation number 1, that quadratic equation, that 9R square minus 48R plus 58 equals to 0. And the general formula for quadratic equation is ax squared plus bx plus c equals to 0. A, b, and c are the coefficients of the quadratic equation, and x is the variable that we are looking for. And we find out the value of x according to the following formula, that x equals to minus b plus minus square root of b squared minus 4 times ac over 2a. In our specific quadratic equation, the coefficient a is equal to 9, the coefficient b equals to minus 48, and the coefficient c equals to 58, and the variable that we are looking for is r. So here x equals to r, so we put the data inside the formula for x and found out the value of r. R equals to minus b. Minus b is minus 48, so b is 48. b is equal to minus 48, therefore minus b will be equal to minus 48, that is 48, plus minus square root of b square. b is minus 48, so b squared minus 48 squared, that is 2304. Minus 4 times a is 9, so minus 4 times 9 is minus 48. 6, and minus 46 times C, that is 58, it is equal to 2088 over 2A. A is 9, so 2A is 18. And 2304 minus 2088 is 216. So in conclusion, found out that R equals to 48 plus minus square root of 216 over 18. So here R equals to 48 plus minus the square root of 216 is 14.6969 over 18. So R equals to, here we will have two solutions that are possible for R. The first solution for R is that R equals to 48 minus 14.6969 over 18. 48 minus 14.6969 is 33.3031 over 18. It is equal to 1.85. So we found out that according to the first solution, R equals to 1.85, but because of the fact that R cannot be less than 3 units and 1.85 is less than 3 units, then we cancel this solution and we left only with the second solution, that R equals to 48 plus 14.6969 over 18. 48 plus 14.6969 is 62.6969, and 62.6969 over 18, it is equal to 3.483. So in conclusion, we found out that the radius of this big circle is equal to 3.483 units. That is, of course, greater than 3 units. And it is true according to our analysis that the radius of this circle can obviously be can be greater than 3 units. The radius of this circle cannot be less than 3 units. The radius of this circle cannot be equal to 3 units, but for sure the radius of this circle can be greater than 3 units. And we found out that indeed that the radius of this big circle, it is equal to 3.483 units. Okay, thank you very much.